All right, we're going to talk about aromaticity right now. This is the next chapter that we're going to look at, chapter 18, and again focus on sections 3 to 5. And our goal here is to look at any molecule and predict whether it's aromatic, anti-aromatic, or non-aromatic. And those predictions will help us understand the behavior of those molecules. So let's talk about 3 important molecules. And again, a lot of what I'm going to talk about is going to summarize what you're going to read in Klein. So there's not a lot new here, but again, this hopefully will help as you think about what things are important when we go to do additional problems. So if we think about 3 important molecules, think about benzene, cyclobutadiene, and cyclooctatetraene, right? Benzene, cyclobutadiene, cyclooctatetraene, right? And the interesting thing about these molecules, right, they're all conjugated, they're all cyclic, they all have p orbitals at every atom, and it turns out, as we know, benzene is incredibly stable. Cyclobutadiene is incredibly unstable, and cyclooctatetraene behaves just like a regular alkene. So we'll just call this sort of normal stability, right? And these 3 molecules fall into the 3 broad classes of stability for molecules. Benzene is what we call aromatic. Aromatic molecules are unusually stable. Cyclobutadiene is anti-aromatic. Right? Those molecules are incredibly or unusually unstable. And normal stability, these are just regular molecules, which are non-aromatic. Right? And when we think about these 3 classes, most molecules are non-aromatic. Right? And those molecules are, let's just say, sort of medium energy. If we're thinking about sort of an energy diagram, those would be in the middle. Right? If we think about anti-aromatic, these things are very high in energy. They're very reactive, they're very difficult to make, right? And there are very few anti-aromatic molecules because they are so high in energy, right? And for aromatic, these are low energy, right? And we're going to see that there are a decent number of aromatic molecules, but most molecules will still fall in the non-aromatic category, right? And so the thing that we need to think about and we need to understand is how can we look at molecules? We don't just want to memorize these 3. How can we look at molecules and figure out whether they are aromatic, anti-aromatic, or non-aromatic, right? And you can read in Klein, there's some very nice description of how we figure this out. It has to do with molecular orbital theory, and there's, again, nice discussion in the book. But let's look at the outcome of that, what the criteria for aromaticity are. All right, so criteria for aromaticity and anti-aromaticity, right? And we have a couple of things here. 1, it must be cyclic. All right, so the molecule must be cyclic. Number 2, it must be planar. Number 3, it must have a p orbital at every atom in the ring. Okay? And if we look at benzene, it's cyclic, it's planar, has a p orbital at every atom in the ring. Same for cyclobutadiene. It looks like that's the case for cyclooctatetraene, but it turns out cyclooctatetraene is actually not planar. It's shaped like that. So that is a non-planar molecule. It exists like that. So that is one reason why that's non-aromatic, right? But clearly, these 3 things apply to both benzene and cyclobutadiene. There must be something else, right? And that other thing is what's called Huckel's rule, right? And Erich Huckel is the chemist who came up with this rule, And that's key for us to understanding what's going on here, right? And it's that the number of pi electrons is critical to figuring out whether it's aromatic or anti-aromatic. Right? And what Huckel said is that molecules will be aromatic if the number of pi electrons equals 4n plus 2, and they will be anti-aromatic if the number of pi electrons equals 4n. And again, for both of these, n is an integer, right? So we're thinking about n as 0, 1, 2, 3, etc. Okay? And again, if we look at this, for benzene, how many pi electrons do we have? We have 6 pi electrons, right? And if we plug it into the equation, that equals 4n plus 2 when n equals 1. Right? For cyclobutadiene, we have 4 pi electrons. That equals 4n when n equals 1. All right? So Huckel helps us distill what you get out of the molecular orbitals down to this really nice set of equations where we can predict benzene aromatic, cyclobutadiene anti-aromatic. Right? And the final point I want to make before we just do a couple of examples is that molecules are always going to exist as the lowest possible energy, right? So that means that if molecules can be aromatic, they will be, and if they can avoid being anti-aromatic, they will avoid being anti-aromatic, all right? So let's just write that out as a key point, right? If molecules can be aromatic, they will be. Again, they will be because that will just be lower in energy. Molecules always exist as their lowest energy form, right? And if molecules can avoid being anti-aromatic, they will, right? And again, it's much better to be non-aromatic than anti-aromatic, right? And we'll see how this is important when we start to do problems. So we'll close with just a couple of examples. In your homework for Monday, you have a bunch of molecules to look at and see whether they're non-aromatic, aromatic, or anti-aromatic. And I just want to show you how I would do that with these 3 molecules, again, hopefully to help as you get ready to do the problems for Monday. So here we have 3 different compounds that are based on 5-membered rings, right? So cyclopentadiene, and then cation and anion, right? And so the question is, are these non-aromatic, aromatic, or anti-aromatic, right? And so if we look at the first one, and it's often helpful to put in the H's. If we look at this one, it's cyclic, it's probably planar, but there's not a p orbital at every atom, right? So if we look there, that's sp3 hybridized. There's no p orbital. So this one must be non-aromatic. Right? If we look at the cation, again drawing the H there, it's cyclic, it's planar. Does it have a p orbital at every atom? Again, when we have a carbocation, we have an empty p orbital. Right? So it satisfies those 3 criteria, right? Cyclic, planar, p orbital at every atom. So now we need to figure out whether it's aromatic or anti-aromatic. So it has 4 pi electrons, and so that's going to be 4 equals 4n when n equals 1. So this one's going to be anti-aromatic. Okay. Unusually unstable, so it'll be very difficult to make that molecule. Right? If we look at the final one, again drawing the H, right? And the question is it cyclic? Yes. Is it planar? Yes. Does it have a p orbital at every atom? Well, it's unclear, right? Where is that lone pair, right? And so we need to look at whether the lone pair is in an sp3 orbital or a p orbital, right? Because again, if that p orbital, lone pair in a p orbital makes it aromatic, then it will be, because molecules will always be the lowest possible energy, right? So let's look at this thing in a p orbital, right? And we can put a question mark if we want. if that lone pair is in a p orbital, how many pi electrons do we have? We would have 6 pi electrons with the lone pair in p. And we've already seen that 6 equals 4n plus 2. This thing will be aromatic with the lone pair in the p orbital. So that's how it exists. The lone pair is in the p orbital, and that's aromatic. Right? And that's really important because that tells us that's going to be an easy anion to make. So this is the sort of strategy that I want you to use when you're working on the problems for Monday, and we'll definitely spend some time talking about those molecules and other molecules.